got another paper here related to symbolic regression. The general idea being you have some system that is generating data, and you want to determine the equations that govern that system. So this paper is called Symbolic Pregression: Discovering Physical Laws from Distorted Video. So pregression, don't worry too much about that word. They coined it themselves as a shortening of pre-regression, which is a step before they actually run their symbolic regression algorithms. And the symbolic regression algorithms they run are the same as AI Feynman 2.0. So discovering physical laws from distorted video. So in this case, the data they're looking at is video of a system, and they want to determine the physical laws that govern an object that is moving around in this video. So again, it's going to be synthetic data. So they're going to generate these videos here, where you have this little rocket that is moving around in different ways according to different laws of motion. And in this case, it's going to be this this oscillator here. So these are the differential equations that govern an object here. So you start with different positions and velocities, and you're going to trace out different curves on the image in terms of each frame you're at a different position along this curve, and we want to be able to run symbolic regression on this data, but this is a very high dimensional representation of this data. So we need to simplify this. We need to somehow extract the useful degrees of freedom out of here to get vectors that we can run the symbolic regression on. And that step is what they're calling this pregression. So here you have these videos that are a sequence of images, and each image is 256 by 256, and you got a whole bunch of those. So it's a very high dimensional input vector, and here we just have 2 dimensions. So we're mapping. We are compressing all this information down into this 2-dimensional representation here. And once we have this, we can run symbolic regression, get these just like AI Feynman. So how do you map these frames onto, in this case, what you're mapping them onto is each frame is going to correspond to a dot on this image, and each video is a trace. So you have a bunch of frames, and they're associated with each other on these trajectories. So we need to map this high dimensional thing into a low dimensional thing. Well, how do we do that? Autoencoders. So this they use pretty standard autoencoder stuff. Bunch of convolutional layers that drop down in dimension to a low dimensional thing here. So let's there's a lot. There's a decent bit going on in this picture. So let's break it up and first just look at this section. So input image. So you got your image here. It's an image of something, and you're running it through a series. You're running it through a neural network to map it into a low-dimensional vector, and then you're mapping that low-dimensional vector back into an image, and you run gradient descent where you're minimizing the difference between your reconstructed image and your original image. So that's how a standard autoencoder works. What is special about this? Well, we're not just looking for how do you we're looking for a very specific latent space. We're looking for a latent space that is well suited to describing the laws of motion. So we need to do a few things to incentivize all of the parameters of this encoder and consequently the decoder to turn the images into a latent space that is simple and well formed for predicting future positions. Because what do you do with an equation of motion? Well, you take the current initial conditions, and you can calculate the next state. So that is what the rest of this is doing. So it's taking this autoencoder and it's copying it a couple times. So now you have this frame here, and then we look at the previous frame. So we got we got the previous frame. So xi is the image at frame I, then the image at the previous frame, and the image at the frame before that. So these obviously get mapped into their own latent vectors. So zi minus 1, and then they have what they call an evolutionary operator. So this evolutionary operator takes the previous two latent vectors and tries to predict the current latent vector. So if this latent space is a good representation of the state of the state of the system, then using the previous two, you can get the velocity, and of course you have the position in that vector space. So with position and velocity, and then U is going to be encoding the forces in the image. With the position and velocity and forces, then you can calculate what the current latent vector should be. And then of course you send the thing through the decoder and you get the reconstructed image. So what's important here is that when you're training this network, you're training it with a loss function that is both that is not just the reconstruction loss. So it's not just the error from the reconstructed image and this original image, but in fact it is it has a whole bunch of terms. So it's going to be that, and it's also going to be the error of the prediction of this latent vector using this evolutionary operator. So let's go ahead and look at their loss function. So the overall loss function is the reconstruction loss, which is the image minus the decoded encoding of the image, and then normalized, So, standard stuff there. Then the prediction loss of that evolutionary operator. So this is the latent space vector, the current latent space vector minus the predicted current latent space vector that you get from the previous two. And then they do mention that they had to divide it by the difference of the previous two latent space vectors, because if you're not careful, this ends up trending towards zero. So if we ignore this for a moment, if z is constant, then u is just going to say, oh, okay, well, we're going to keep it the same as zi minus 1. So then you're going to have zi essentially minus itself. And so you're going to have zero prediction loss, but you're not actually getting anything useful out of it. So it's putting this scaling on there tries to push it away from that state. So then they also have some terms for what they call Pareto optimality. So this is penalizing complexity. So they're calling this their nonlinearity loss function. And what they're doing is they're taking the gradient of the Jacobian of the evolutionary operator. So J here is the Jacobian of that mapping itself. So this function u, we're taking the Jacobian of that, and the Jacobian is a matrix with partial derivatives. So the idea here is you're trying to minimize the complexity of the laws of motion. So what u is doing, u is approximating the laws of motion. And you want to bias it towards simpler laws, because of course there is an infinite space of functions that just as accurately calculate or predict or fit data. You can always add extra terms. If you have a linear theory, you can always add like x to the 12th terms, and like the if your epsilon is small enough, anything over like squared goes away. So that you really want to prioritize simplicity as you're trying to build this map. Also, you're trying to push this whole system into a state where the vectors, or the latent space here, is well suited for simple laws of motion. As simple as is possible. So why this gradient of the Jacobian? Well, they take inspiration from general relativity, because Max Tegmark is a physicist, and oh man, whenever I get a look at my good friends, the Riemann tensor, and anyway, so the idea here is spaces that transform tensors in more complicated ways it's analogous to having a high degree of curvature. So since we can actually build a metric out of the Jacobian, because a metric, it's not the metric itself really, it's these guys here, these gamma matrices. They tell you how to when you when you take a derivative of something on a curved surface, you have to account for the directions changing. Anyway, I don't need to jump into covariant derivatives here, but the idea here is there's this analogy between between these mappings of latent space vectors onto other vectors in the same vector space, that is very similar to how you transform vectors or tensors in general relativity. And so they first talk about using this squared curvature term, and the so the way they build this curvature term is they take the Jacobian, it's the dot product of the Jacobian with itself, and then they build these gamma matrices, and these gamma matrices they're built from derivatives of the metric. So each of these commas here, those are derivatives with respect to those indices, and then the same thing up here. So the Jacobian itself is a bunch of partial derivatives. Then you take more derivatives here, and then you take more derivatives here. So you end up taking third derivatives, and that ends up giving you a scalar. You can also just do the general, like the normal scalar curvature. I don't know why they want to go for the squared curvature, but that's neither here nor there, because immediately after saying, oh hey, let's take the curvature, they say, oh well, it has these third derivatives, and that's really, and it's a really big, this is like what is it, 16 equations there. So I guess we're in 2 dimensions. So anyway, it's a really complicated thing. So instead, analogous to that, they say, let's take the Jacobian, which is those partial derivatives, and let's take the gradient of that. Just to note that this W here, that W is simply taking those previous 2 latent vectors and putting them into a slightly higher dimensional vector. So this will encode both position and velocity in it as yeah. Anyway, yeah. So and then that's the nonlinearity term. They also have this acceleration term, and so the idea here is, you want to minimize the amount of acceleration, because things accelerating too rapidly are non-physical. So if you have noise, the noise might like suggest that there's a really high acceleration, but you want to kind of force it to be nice and smooth and continuous. So you're saying, hey, if let's in some sense, this is like the change in the velocities. So you're trying to penalize that a little bit. You gotta be careful with that though, because like when you look at that very first equation they show us, this is acceleration right here. That's the whole thing. It's fairly simple acceleration, and it's like not extreme acceleration. Like you're not seeing things like instantaneously change direction, which maybe is kind of the goal of that term. So those are the different parts of the loss function. They do also mention a problem with topology. So for all of these things, the latent space they're interested in is two-dimensional. But you have to be careful when building a two-dimensional latent space, because your initial guess for the latent space is going to be terrible. It just is. Like you're always going to be initializing your the parameters of your network to be random, and then you try to learn a good representation. The problem is that in 2 dimensions, you're trying to smoothly deform these paths, and like you can't take 2 paths and cross them and smoothly cross them and like pull them apart. You end up having things analogous to knots in the latent space, and that prevents you from learning a really good latent representation. But this here is really interesting. So where is it? Here it is. Let me make that smaller. This guy right here. So there is a theorem in knot theory that says you can't have a d-dimensional knot in an n-dimensional space if n is greater than 3/2 one more than the dimension. So in this case, we are looking for a two-dimensional latent space. Really, we want to avoid two-dimensional knots. So 1 plus 2, 3/2 of that is, I guess, 3/2 of 3 is going to be 9/2, and that's a little bit more than 4. So what they end up doing is they initially start with a latent space that is so they initially start with a latent space that is 5-dimensional. So it's still like going from a very high dimensional thing to a still exceedingly low dimensional thing. So now this is going to be 5-dimensional, 5 dimensions. And then they do some initial training with this latent space at 5 dimensions. And then they run PCA, principal component analysis on that, which is this here. So now they have 5 dimensions instead of 2, and they know that there are really only 2 dimensions that they're interested in. So you run principal component analysis on it, and you say, oh, these are the 2 degrees of freedom that are the most important. So let's so we have this learned latent space that can smoothly deform and across itself, and we can get nice global minima for simplicity of all these things. And then once we have that, then we say, okay, let's look at this 5-dimensional thing and let's slice it where we have the 2 interesting dimensions. So then they go ahead and they look at that. So that's a really interesting very clever way of getting around that topological problem. So that oh yeah, there's one more thing here. So it turns out that when they do that, the latent spaces that they learn for any different equations of motion end up being related to each other. So in this case, these were just rockets moving with constant velocity. These were rockets moving under a simple harmonic oscillator. And the learned latent spaces for these are very similar. And in fact, they are only different by an affine transformation. So an affine transformation is going to be something like this. So it's going to take a vector, it's going to multiply it by a matrix, and then add another vector to it for some general matrix like that. So they draw another analogy here with that to general relativity, because this is a coordinate invariance, and they then use the fact that these are related by affine transformations to then further learn the simplest the simplest representation by learning the best affine transformation to minimize complexity again. So these are different latent representations from the different from 5 different equations of motion that they were learned with, and then they have these different sub-affine transformations. So affine transformations are like it's like the set of like conformal transformations and plus another couple things. So they got vertical shifting, horizontal shifting, rotation, and shear. So it's learning the best rotation, the best shifting, and the best shearing and shear angle, to simplify the complexity of the found equations. So what is kind of the big picture of all of this? Why should you care about all of this? So yeah, sure. Like you got these latent spaces, these two-dimensional latent spaces that are similar to the original traces of just following equations, and then from those you're running symbolic regression on those. Sure, but why really care? Well, it's because like these images or these videos, they don't need to be videos. Like they can be anything. Like any general high-dimensional data source run through a similar thing. Run through this this kind of autoencoder down to a low-dimensional latent space. Throw in some PCA there just for fun, and then you run symbolic regression on that latent space. Like you should be able to take general data and extract equations, not just nicely formatted data like we had with AI Feynman, but a much more general kind of data. Now of course, like you're gonna have to still handcraft things for most individual types of data, but this kind of approach, I mean, maybe there are ways of abstracting it so that you don't have to, but if you have these are two-dimensional images, So say they were three-dimensional lidar scans or something. You could probably do a similar kind of autoencoder with just a more with three-dimensional kernels and all that. But yeah, you can find equations of motion or other equations governing systems from videos, images. Well, like in this case, we want multiple images, or you'd have like videos of lidar scans. Maybe it's a maybe we're looking at sound waves. So maybe we're looking at snapshots of sound waves being recorded from something, or maybe we're looking at traces from the signal from I don't know. I want to say binary black hole mergers, but those who's gonna get their hands on that? I don't know, like radio frequency bursts from pulsars. Like the it this kind of approach says like, yo, the form of the data like doesn't need to be all that special, because you can learn the lower dimensional representation of that is going to best be suited to figuring out the equations that govern that system. So that's I think this whole series of papers with this guy and Max Tegmark, because Silvio, he was also on the AI Feynman 2.0 paper. He's first author on that, actually. So the entire series of papers by these guys, I think it's really important to being able to build to build tools that tell us about the data instead of just telling us predictions. That's kind of, maybe I focus a little bit too much on how important that is, but I really think it's important. I like you look at, and you don't need everything to be explained. Someone builds a PID control loop for their quadcopter. I don't care if the parameters for that PID control loop were learned empirically. Essentially it's even if the person was doing it manually, it's still like an internal gradient descent kind of logic that they're going through as they're nudging the values of that control loop around. I don't care about those values there, but the idea that, like, okay, proportional, integral, and derivative, I need to account for the momentum. I need to have some way of having small errors eventually build up so that they can nudge the they can nudge the value up, so that the small errors don't accumulate and you drift way off. That's the kind of explainable AI we're looking for. We're not looking for someone to be able to explain autopilot to a 2-year-old. We're looking for ways that we can look at these neural networks or these, in this case it's just a big pile of data, and figure out something that means something to us. So yeah, I'm gonna keep going with different papers like this, and yeah, feel free to ask questions. If you happen to be one of the authors of this paper, feel free to reach out. Anyway, yeah, I'll be back with another paper sometime soon.